This question is concerned with terminal velocity and a parachutist that has just left the plane. First of all, you need to draw a free body diagram of each stage of the descent of the person falling under free fall. First of all, the weight is the only force acting on the person. There has been no time for the object to accelerate yet, so it's just weight. So weight is much greater than air resistance. Then, as the object has descended, time has passed, acceleration due to gravity has occurred, and the person is travelling a bit faster now, and so there is some air resistance. Okay, but weight is still greater than air resistance. So the object will still be accelerating, but not as fast as before, because the resultant force is smaller than before. Then you get to the situation where the object is descended more, time has passed more, acceleration has acted on the body. Now, weight is not so while the object is still descending, terminal velocity has been reached. So no overall velocity of weight is equal and opposite to distance. So we now go to the graphing of this. So you can see my three diagrams above represent different parts of the graph. So to start with, weight only is acting. That's when you have the biggest acceleration, and therefore the velocity time gradient is the steepest. Then, because air resistance is acting, acceleration is not so great, and the gradient levels off. And then at terminal velocity there is no gradient because the line is flat, it's just plateaued. Okay, so the graph underneath shows acceleration and the variation of acceleration with time. So acceleration is greatest at the start of the descent, where weight is much larger than air resistance. And that shallows and plateaus until at terminal velocity there is no further acceleration because the constant velocity has been reached. Weight is equal and opposite to air resistance, no more acceleration. Okay, so now we're looking at the part where the parachute has been deployed. So the parachute's gone up, the object is still falling, but air resistance is massively increased because there is a huge surface area of the parachute, and so there are many more collisions of the air molecules with the parachute. So air resistance is greater than weight. Resultant force is now vertically upwards, which is opposing the motion, so there will be a deceleration, so the object will start to slow down. Okay, as it slows, the air resistance decreases because it's slowing down. So the top arrow will reduce and reduce and reduce until once again weight is equal to air resistance. And that is, I think, the most challenging part of this conceptually. Okay, and then you have a second terminal velocity whereby weight is equal to air resistance at a lower speed. So if you have a look at the graphs after the parachute has been deployed, you've got a velocity time graph on the top and an acceleration time graph underneath. So the velocity time graph shows a decrease in speed, okay, until a second terminal velocity is reached. And the graph underneath is showing you that the acceleration is negative because it's decelerating, and that then reduces to zero, or increases to zero if you prefer to see it that way. So you can see on the two right hand side graphs you've got a velocity time graph and an acceleration time graph of the whole of the descent. So the top one shows the velocity increasing as the parachutist has jumped out and is getting faster and faster, albeit the acceleration is declining until it reaches the first plateau, where weight is equal to air resistance, equal and opposite. And then after the plateau, then you have a big decline in velocity as the parachute is deployed to reach a second terminal velocity. And then the final graph on the right at the bottom is showing the acceleration time graph for the whole of the descent. I hope that helps you to answer problems that you had with the assessed homework.